Hi, everyone. My name is Kevin Eccles. I'm a graduate student at Princeton University working with Professor Ali Yazdani. We do STM at Princeton. And today I'm really excited to show you some new results that will be appearing in an archive preprint that's posted tonight, where we've uncovered a number of classic signatures of spectroscopy that point us towards unconventional superconductivity in magic angle twisted bilayer graphene. So before I get into the results, I'd like to introduce the team. This is Myung-Chul Oh. He's the lead author of this new study, and he's a postdoc in our lab. Together with Myung-Chul and Dylan, we've done all the experiments that I'll be showing you today. Ryan has just joined our team and is learning the trick of the trade, and I give thanks to my advisor, Ali Yazdani, for supporting us and helping us along the way. So just a brief outline of the talk that I'm giving here today. I'd like to introduce the problem at hand. There's an ongoing debate as to whether or not superconductivity in magic angle graphene is conventional or unconventional. I'd like to point to some basic spectroscopic features of the superconducting state in magic angle twisted bilayer graphene, specifically when we hole dope the system in the lower flat band. We'll need to be able to clarify or classify whether or not our samples are superconducting or not. And so we complement our STS experiments with point context spectroscopy, which is done in a gate tunable sample for the first time here. These two experimental techniques will tell us a lot about the sample, and we'll be able to make comments about the pairing symmetry and about the existence of some other high temperature precursor phases like a pseudo gap regime. So this will tell us that, we'll have evidence from both of these probes that superconductivity in magic angle graphene is nodal. It's an anisotropic pairing mechanism with nodes in the wave function, and that there's a high temperature and extremely high magnetic field pseudo gap regime, which appears when coherence is quenched at these two critical parameters here. Finally, I'd like to show a little bit of preliminary data at the very end, where we've looked at a magic angle graphene aligned to boron nitride substrate. In transport experiments, people do not see superconductivity, and indeed our two-probe technique shows that there is no superconductivity in this system. So we'll shed a bit of light on what might be needed for superconductivity by analyzing this system and comparing it with unaligned devices. So without further ado, let's talk about the nature of superconductivity as seen through transport. Original experiments from Pablo Carrillo Herrera's group at MIT have shown that superconductivity occurs at extremely low carrier densities. This is already calling into question the nature of the superconductivity in this system, given this is a kind of a mismatch of energy scales required for BCS theory. It also occurs in a phase diagram that's kind of broadly similar to that of the cuprates. We see at 2 holes per Mori unit cell, there's this insulating phase, a correlated insulator, and then on either side, there's this superconducting dome feature. So if superconductivity inherits some sort of traits from this insulating phase, then it may be mediated by some exotic bosonic glue similar to that proposed in the cuprate superconductors. So this is definitely pointing towards an unconventional nature, but I'd say that more recent experiments have pointed us towards a more conventional nature to superconductivity. So I'd like to point out the work of the Evitov group and the Young group at ICFO and UC Santa Barbara, respectively, where they've taken magic angle graphene and separated it with a very thin HBN substrate from a underlying graphite backgate. Bringing this magic angle graphene close to the graphite effectively screens out long-range interactions. And in this device structure, you see robust superconductivity in the absence of insulating phases. So insulators seem to need this long-range Coulomb interaction, but when you partially mitigate the Coulomb interactions, you see superconductivity with similar TC to those in non-screen devices. So this may point to the fact that superconductivity is only a result of maybe the high density of states of the flat bands. These Moiré systems, they generically have very, very high density of states. And so with some electron phonon coupling, you'll find a moderate TC in these systems. Additional experiments from Leo Lee's group at Brown have shown that if you take magic angle graphene and embed it in a device where you also embed a Bernal stack bilayer graphene. Now we'll use this for an in situ tuning of the screening potential, effectively tuning the chemical potential in bilayer graphene in order to tune the screening of long-range interactions in magic angle graphene. So if you take this device structure, you place the chemical potential in the gap of bilayer graphene, very little screening is going on. And you see superconductivity just below 2 holes per more array unit cell. And as you increase the screening, you place the chemical potential in the metallic region of this of bilayer graphene, then you see superconductivity is more robust. It's more robust by nearly all metrics. The critical field increases, critical current increases, critical temperature increases, and the broadness of the density range at which it is seen is increased. So nearly all metrics are pointing towards screening being essentially favorable for magic angle graphene in a very nicely tuned platform. So maybe superconductivity is just phonon mediated, and it's competing with other correlated phases. When I kill those correlated phases, then superconductivity takes over more of the phase diagram. So I think that these are really nice experiments in the early field. These are good results for us pointing towards the nature of superconductivity, but I invite you to step back a bit. This is a new field, Moray flatband physics, and there is precedent in other unconventional superconductors, specifically spectroscopic signatures, kind of classic signatures of unconventional superconductivity from angle resolved photoemission spectroscopy and scanning tunneling spectroscopy. ARPA's experiments have shown that we can identify, if you look at the gap structure in a cuprate superconductor at along the Fermi surface, you'll find there's a fully gapped feature at, say, 0 degrees along the Fermi surface with respect to some high symmetry line. And then as you move 45 degrees away along the Fermi surface, you see a nodal minimum here. So this is indicative of a D-wave gap symmetry, which is unconventional in the system. In a more modern manifestation from the ZX Shen group at Stanford, you can really see in laser-based setups, the linearly dispersing quasi-particles are kind of unequivocal here. So this is really telling us something intrinsic about the gap symmetry that cannot be explained by an isotropic BCS mechanism. In addition, scanning tunneling spectroscopy has been indispensable to this discussion in the cuprates. When you do STS at low temperatures on a cuprate superconductor, you find this large gap with kind of broader coherence peaks and a nodal V-shaped or U-shaped minimum. And as you warm up the sample, you'll find that even as you pass through TC, there's still a strong suppression of the density of states at the Fermi level. This is indicative of a precursor pseudo gap regime that is kind of taking over the high temperature phase diagram of the cuprates. And again, in a more recent manifestation from my own advisor, Ali Yazdani, if you take a cuprate superconductor with a transition temperature of 93 Kelvin, and you measure it above the transition temperature, something like 120 and even 140 Kelvin, you see significant portions of the sample that show a pretty large gap, which is definitely showing the kind of correlated short-range puddles of superconductivity that form in these systems. So I think, given these experiments on the cuprates and how elucidating they were in understanding conventional versus unconventional superconductivity, we set out to do the same experiments on magic angle graphene. And so this, our study marks the first of these studies that shows that local spectroscopy is able to identify a number of so-called classic signatures. These will be signatures of a V-shaped gap, a very large gap that emits a large gap to TC ratio, and the presence of a high temperature and a high field pseudo gap regime in this system. These are signatures of unconventional pairing in magic angle graphene, and some of these signatures are quantitatively inconsistent with a BCS origin. So I invite you to read this preprint that will be out later tonight. So in order to get started, let's discuss just the fundamental aspects of spectroscopy in the superconducting regime of magic angle graphene. So, we're doing spectroscopy on gate tunable devices. I have magic angle graphene on top of hexagonal boron nitride, and we bias the sample with a sample voltage Vs, which gives me energy resolution, and gate voltage Vg, which gives me density resolution. And so we're measuring the tunneling current or the differential conductance of this tunnel junction with respect to these two variables. So generically, we're producing these 2D color plots where density is changing along the y-axis, energy is changing along the x-axis, and this center line is the Fermi energy. So nearly all action, correlated insulators, churn insulators, and superconductivity are going to occur right around this Fermi level and are going to appear as blue features. These are zero conductance, suppression of the density of states at the Fermi level due to either an insulating gap or a superconducting gap, which we'll be able to distinguish. In addition, we're performing these experiments on a homemade, home-built STM, the newest of Ali's suite of instruments, called the ultra-low temperature scanning tunneling microscope. This is a dilution refrigerator STM with a vector magnetic field that I helped build with some of my colleagues. The thing I want to point out is this spectrum here. So whenever you build a new STM, you need to calibrate the STM and calibrate specifically its electron temperature. You want to know how cold are the electrons given the wiring that I did. And so you take a differential conductance proportional in the single particle limit to the local density of states. You'll do this in the superconducting regime of a known superconductor, like aluminum. Aluminum has a TC of 1 Kelvin, which is about the same TC as magic angle graphene. And you can clearly see this S-wave gap in aluminum here. So there are very sharp coherence peaks and a flat, hard bottom. And by fitting this, we can tell that our electron temperature is a little below 200 millikelvin, and we can measure gaps well below 200 micro eV. So if MATBG is a BCS S-wave superconductor, then this is the gap that we expect to see in the system. And we have clearly enough energy resolution to do so. So we're working with about 50 micro electron volts of energy resolution as shown in this measurement. So let's jump into it. Gauge-tunal spectroscopy on magic angle graphene shows in the lower band, where superconductivity is most robustly seen in transport experiments, we see a gap phase that opens up around nu equals -2. This is 2 holes per more unit cell. It closes and reopens into a new gap that persists a little beyond nu equals -3. We see this same structure in a total of 5 devices now, and it shows, these gap phases do not exist at our highest temperatures available, and so we know that these are zero field ground states in the system. This gap in particular is kind of interesting because it's coincident with the densities that are marked to be superconducting in transport experiments. So if we take line cuts in these differential measurements here, we'll see what a single spectrum looks like at a particular gate voltage. Here are 2 spectra from 2 representative devices. Spectra vary amongst devices, and so in our manuscript, we're showing a number of devices to give you the most universal features of spectroscopy in the system. So I think there are 2 aspects that we should identify in these spectra. The first is that they're generically V-shaped. So in device A, we see these sharp coherence type features that come down to this nodal minimum. In device B, we see much broader coherence type features that come down to a zero bias conductance minimum here. The second thing is that the tunneling gap is enormous compared to the transition temperature of these superconductors, which we're able to locally measure to be about 1.2 to 1.3 in our devices. Remember that aluminum is also in this range of transition temperatures, and it has a gap of about 200 micro electron volts, and yet we're finding gaps as large as 900 or even 1400 micro electron volts, which admits local pairing criteria 2 delta over kVTC as high as 25. In BCS theory, this is a mark to be, you can calculate this to be about 3.5. In systems where there are strong electron-phonon interactions through Eli-Ashberg theory, you'll treat it a little bit more carefully, not as a weak coupling theory, but a strong coupling to phonons. And this ratio can be as high as 5 or 6 in some lead and bismuth based alloys. Never as high as 25. So this is really crazy in the system. And I think that there are 2 ways to interpret this. We should be careful that this may be a pseudo gap regime. These are common amongst correlated superconductors. And so I think there are, again, 2 schools of thought. The first idea is that maybe this is the superconducting gap. And if this is the superconducting gap, I should be able to fit it to a modified BCS density of states. And so this is what we do. We fit it to a nodal model here, and you can see very nice characterization of the gap as a function of energy with this nodal fit. And you see a poor characterization from a nodeless superconducting model. I should note that this model is a little bit better when you include enormous quasi-particle broadening, unphysically large quasi-particle broadening. So I think that the statement that we want to make is, if this is the superconducting gap, none of the samples that we've seen resemble the isotropic S-wave prediction from BCS theory. In fact, in contrast, the second school of thought is that no, this is a pseudo gap regime. This is the pseudo gap. This is way bigger than the superconducting gap, and there's some smaller gap that's forming at low energies. And so, precedent from the correlated superconductors of the cuprates is that you should fit the low energy characteristics. That the low energy characteristics of spectroscopy in cuprates, especially underdoped cuprates, where there's a kind of a large temperature range for pseudo gap regime, is that the low energy density of states still characterizes the nodal quasi-particles of the system, and that high energy states characterize the pseudo gap regime. Although we don't see a difference, like a change in slope, like they do in the cuprates, we still perform this study. We perform it as a function of gate. So here's a number of gaps that we see at low temperature, and we fit every one of them at different gates throughout the superconducting dome to a nodal hypothesis and a nodeless hypothesis. And you'll see at every gate voltage, nearly every gate voltage, the fits are much better at low energies than they are of the nodeless hypothesis. So I'd say that even in the case where this is a pseudo gap, I think low energy density of states is aptly characterized by a nodal gap function. I should stop here. And one thing is, kind of crazy is that I've kind of skipped over a really essential part of this study. And it's that how do we even know the sample is superconducting? Early results from Pablo Herrera's group showed that you can have correlated insulators. You can have magic angle graphene systems that are a little bit more disordered than most modern samples, and they don't show superconductivity. In addition, there's some non-trivial understanding that the tip is, the STM tip is a huge metallic object. It's a massive piece of metal that you bring about half a nanometer from the surface. And so if electron-electron interactions are favorable to superconductivity, the tip may be screening it out, or it may be distorting the local potential or something like this. So if I see a gap even in the carrier density range of superconductivity in my samples, I need to be absolutely sure. And I think this is really stemming from the fact that this behavior that we're observing is highly unusual. And I think we need to be very confident that this is a superconducting state that we're probing with scanning tunneling spectroscopy. Namely, the gap is V-shaped. This is a pretty big claim here that there may be nodes in the superconducting gap wave function. The gap is enormous. I've already told you it's not expected to be this big for a 1K superconductor, and this needs explanation. It also, in later slides, I'll show you, it persists to much higher temperatures, as high as 5 Kelvin. And much, much higher magnetic fields as high as 6 Tesla. These are way, way higher than anything that has been observed in transport experiments. And so already there are a lot of pieces of evidence that are disfavorable to this, that no, we may be not even probing the superconducting state. So we need a probe that will really tell us this. When I tell people this, when we didn't figure it out, essentially, I tell people this at conferences. They ask, why can't you just measure the resistance? The resistance of the sample in transport shows a very nice second order transition and a hard bottom at 0 resistance in magic angle graphene superconducting states. I show you that, here is a geometry that I've kind of schematically shown where if you were to run current through these 2 leads and measure the voltage drop over here, you would measure a 0 conductance state. And although, an STM tip over here would see superconductivity, if you were over here in the sample, then you would see a gap in the system. It would be an insulating gap, and you would wrongly describe the superconducting properties of magic angle graphene. So this is all to say that global transport experiments are not helpful in distinguishing local spectroscopy gaps. It's just not something that you can use in the system and be fully confident that you're probing the superconducting state. In addition, there are a couple of existing experimental techniques for locally identifying superconductors, the most common of which is to image a vortex lattice. I place a small magnetic field over a 2D superconductor or into a 2D superconductor or a type 2 superconductor, a bulk one, and you'll find that the in-gap states that appear because of the magnetic field form a triangular lattice. These are quantized vortex cores that are sensed by scanning tunneling spectroscopy, and the gap looks different in the middle of this core as it does in the outer core. So you can directly image these things with STM as shown. This is the superconducting vortex lattice of another 2D superconductor, niobium diselenide, as taken by the Hanaguri group at Riken. We tried this and it failed. I'll be really honest, it seems that this is a very difficult experiment in this setting, not only because the samples are generically dirtier than cleaved crystal, but even when we found enormous clean areas, we were not able to see any vortices. I kind of speculate that maybe vortices in these systems are being pinned by disorder, pinned by atomic impurities, and that graphene, as grown by Mother Nature, is essentially perfect. There are very, very few defects, if any, that we've seen in magic angle graphene. And so it may be that these vortices are just sliding around the local tip potential, that the tip admits some kind of a work function slight mismatch and then causes them to move around, especially in such a gate-tunable sample. A second way to do so is to use scanning Josephson spectroscopy. This is when I take a superconducting tip and a superconducting sample and measure the Josephson peak between them as a superconducting insulating superconductor junction. So here is some data from past lab mate Malika Rendaria and Ben Feldman, who were a part of the Yazdani group, who used a lead tip and a lead surface. And find a very sharp zero bias conductance peak and a number of oscillations attributed to other photon-assisted modes in the system. So this is an interesting perspective. We didn't try this, and because we didn't do so because there are some technical difficulties here. I really need to know that the place underneath my tip is superconducting and be able to measure the superconducting gap. I need to be able to do these things with the same tip, and so I need a normal metal tip to measure LDOS, but I need a superconducting tip in this case to measure whether or not it's superconducting. And so you would have to apply a small magnetic field. The gap would change as you kill superconductivity first in your tip and not the sample. BC is very low in magic angle graphene, and so that's kind of difficult already. But even so, you need to find something, some superconductor that is killed at a low enough field, but also is relatively work function matched to the sample. And so we were not able to kind of identify something like this that would be feasible, but we did it in a different way. And I think that this is the probe that we'd like to discuss. Is there needs to be a new way to unequivocally distinguish in gate-tunable spectroscopy the difference between a gapped insulating phase, which appears here at n equals -2, and a gapped superconducting phase, which we argue appears here below n equals -2. So the key to this experiment here, and the difficulty that we faced for 2.5 years in order to find this probe and really characterize, first develop the probe and be able to get really nice data with it, is to combine scanning tunneling spectroscopy experiments with point contact spectroscopy experiments using the same normal metal tip. So the key is to realize that local spectroscopy falls on a spectrum of barrier strengths here. So we'll characterize barrier strengths via this dimensionless parameter called Z, where Z large just means we're in the tunneling regime, and Z equals 0 means you're in the transparent barrier touching regime here. So, having the SDM tip about 0.5 nanometer above the sample, we find quantum mechanical tunneling where electrons are emitted on this quantum mechanical barrier. And although the energy is high, it tunnels and exponentially decays the wave function into the sample and measures LDOS in an S-wave superconductor that looks like this here. So you should see these sharp peaks in the density of stakes around the gap edge, and then a hard bottom minimum that's indicative of the superconducting gap in the system. As you lower the tip into the sample very carefully, you find that more in-gap states fill in. And these are not the same in-gap states as you would see in, say, the middle of a vortex lattice. These are in-gap states that appear due to the reduced height of the tunnel barrier here. So once you make point contact, spectroscopy is not defined by quantum mechanical tunneling, but defined by a very, very thin barrier in the limit of Z equals 0, where electrons emit on the barrier and they see the gap state to single particle excitations in the superconductor. So this electron can't go into superconducting magic angle graphene, but what can go in is a Cooper pair. And because of the phase coherence of the bath, the electron emits on the barrier, it emits a Cooper pair with 100% transmission and reflects back a hole. So this process is called Andreev reflection, and it's used in many superconductors to identify energy scales associated with superconducting behavior using point contact spectroscopy, because again, you see out at high biases, both electrons and Cooper pairs are viable excitations. And then as I approach the interior of the gap, electrons are now forbidden from the system, but 100% transmission of Cooper pairs exists. And so we see a doubling of the normal state conductance in an S-wave superconductor with particularly a negative second derivative, or a negative third derivative, actually. It's a peaked system, a peaked spectrum in this characterization. So I'd like to discuss a little bit of the locality of point contact spectroscopy. This is now clearly a way that we can measure the difference between insulating samples and superconducting samples. In insulating samples, you can do a little bit of calculation, and you'll find that it's so-called 1/r local. So if you divide up the sample radially around the tip into small little differential elements, you'll find that the two-terminal conductance, as I place the tip into the sample and measure the conductance from the tip to the sample contact, it's particularly sensitive to what's underneath your tip. And this is kind of natural, that if you have a little insulating puck of sample and mostly conducting around it, and you touch that little insulator, then the conductance, the two-terminal conductance, all has to go through that little puck that you're touching. But if that puck is just a little bit off from your sample and you touch the metallic sample, then all the resistances add in parallel, and so the electrons, the current will flow around the insulating phase, and you really won't be able to sense it. So in insulating samples, it's 1/r local, and you can see from early, recent experiments that were posted on arXiv from our collaborators, our teammates, Xiaoming Liu, Gelera Farahi, and Chengli Chu. They were the first ones to do this in our group, where they placed the tip into the sample and measured the two-terminal conductance, and you can see really well-developed quantum Hall states. This is the composite fermion sea and a hierarchy of Jane states that appear in the zeroth Lambda level of graphene. So they did this first in our group, and we saw this data and saw that it was really exquisite quality for insulating states, and thought maybe we can do this for superconducting states. In superconducting states, the resistance is low, and so this is not 1/r local anymore in the calculation in our supplement. But the analog is that in superconducting states, there's an interfacial state. It's the Andreev state that you probe into. So you find that spectroscopy as a function of bias using this point contact in superconducting samples is local to the coherence length of the sample. So if I touch within one coherence length, then I'll tunnel coherently into the superconductor via Andreev reflection, and I'll see this Andreev spectrum in bias resolved spectroscopy. So in total, we're interested in using this new probe, this combination of scanning tunneling spectroscopy and point contact spectroscopy, as a novel probe for phase coherence in 2D superconductors. When you do scanning tunneling spectroscopy, you'll see a gap shape that tells us something about the pairing symmetry. But in order to classify whether or not this gap is insulating or superconducting, we use point contact spectroscopy right after. We lower the tip into the sample and touch to make point contact, and then measure this characteristic right after. So performed on magic angle graphene, you see scanning tunneling spectroscopy shows a number of pre-described features here. So there's an insulating phase at 3 and 2 and -2 electrons per more unit cell. And then there's a gap that opens up below that we think is maybe correlated to superconductivity. It's clearly coincident in density with superconductivity. And yet, if you perform point contact spectroscopy on the same sample, you just literally touch that same AA site very, very gently, then you'll find insulating, non-ohmic, zero conductance behavior at the insulators, 3 and 2 and -2. But you'll find this peaked value, the Andreev reflection signal, around Newgall's -2 to -3. This is indicative of the superconducting state of the sample. And it's in direct correspondence. You see the one-to-one correspondence between the gate voltages. Although there are many states that we see are gapped at the Fermi level using scanning tunneling spectroscopy, this density range between Newgall's -3 and -2 is the only one where we see a U-shaped or V-shaped gap in spectroscopy and the Andreev signal, which really confirms that we're in the superconducting state when we take the spectroscopy. When you do this experiment as a function of gate bias, or sorry, as a function of energy, you can see this peak-like feature at something like 300 millikelvin. And then as you increase this, the temperature, the peak drops into a normal density of states around 1.3 Kelvin, which tells us what the local TC of our sample is. here is a gate bias sweep where we're changing the density and doing it for every density as a function of energy. And you can see this kind of sharp enhancement of the conductance and peak-like feature goes away at TC, very similar to the experiments done in transport. So this is really nice that it agrees in temperature, and in fact, it agrees with field as well. So if you take this point contact Andreev reflection signal, you can see it's peaked at 0 Tesla, and then as you increase the field to something like 50 millitesla, it goes back to normal and becomes a little bit insulating at 200 millitesla. So this crossover, when you see the Andreev feature and then it disappears at critical field of 50 millitesla, we're in the same ballpark range as transport measurements. So, now that we have these two probes, I want to, talk about how we can compare the two pieces of information, and they'll act kind of complementary to one another in telling us that there is evidence for nodes in the superconducting gap of twisted bilayer graphene. So just so we're on the same page, when I do spectroscopy as a function of gate in the superconducting regime, we see in a nodeless scenario, we would see this kind of hard gap spectrum with sharp coherence peaks in DIDV. And this is because in the S-wave case, the gap is symmetric around the whole Fermi surface. And so everywhere in momentum space, there's the same gap. And so when I integrate all these gaps together, I get this averaged gap here. In the case of a nodal superconductor, such as a D-wave superconductor, the gap varies as a function of angle along the Fermi surface. And so, at anti-nodal directions, we find a full gap, which would look kind of like in this direction, an S-wave gap. And then as you approach the nodal direction, you get smaller and smaller gaps that appear to look essentially normal in the differential conductance here. So when we integrate across this whole sample, we get something that looks kind of V-shaped, which is the sum of all these gaps here. So back to the fits that we did of the superconductor. Now we know that this spectrum is taking it in the superconducting state of MATVG, and we find that, again, the nodal gap fit with a single slope all the way down to a nodal minimum is really characteristic of the system. Again, tunneling spectroscopy varies among sample to sample, but none resemble the isotropic S-wave prediction that we showed schematically in 2 slides before. Now, if you do this same experiment with point contact spectroscopy, you'll find that point contact spectroscopy is also pairing symmetry sensitive. That similarly, there's twice the conductance, the normal state conductance within the gap in point contact spectroscopy, because electrons emitted on any in-plane direction along the gap experience the same superconducting gap, and so they all look the same when I integrate across this Fermi surface. In contrast, we'll find kind of a peak structure, a rounded peak structure, when we integrate a large gap directions in the antinodal direction and no gap directions in the nodal direction. So when I take the integral here, it looks more like this in point contact spectroscopy, where this top zero bias conductance is still indicative of a twofold increase in the normal state conductance. So if you perform measurements with point contact spectroscopy, we find that here is the Andreev reflection in device A prime. We find that the S-wave fit is poor at lower energies. It really doesn't capture the pointiness here. In this situation, we're using pretty large quasi-particle broadening and this kind of unrealistic tunnel barrier. It has to be 0, and if it's anything higher than this fit gets way worse. So in situations where there's a perfect tip sample junction, we would not even be able to reproduce this. Whereas the nodal gap fit produces a much more reasonable 0.1 Z in the tunnel barrier strength and has a much smaller quasi-particle broadening. So, these deviate from the isotropic S-wave prediction, but I don't want to hark on this point because they are similar. I will admit that they're very similar, but I think that the nodal gap fit fits a little bit better. And in conjunction with the tunneling gap, we can find that there's evidence that is consistent between two probes that the superconducting gap function in magic angle graphene hosts nodes. In addition, when we do these two fitting procedures on the Andreev spectrum and the tunneling gap, we get vastly different energy scales for the system. So what I'm calling the Andreev gap delta AR is effectively a measure of energy coherence. In the cuprate superconductors, this tells me something about coherent pairing below TC. This is the energy scale that defines that setting. And we find that even this energy scale is a little bit bigger than what you would see in a normal S-wave superconductor. BCS mean field ratio for 2 delta over kBTC should be about 3.5, and we find something about 6 for the coherence here. But in contrast, when you do tunneling spectroscopy, this is effectively probing the single particle energy spectrum. It doesn't have to reflect the coherence of the system. It may reflect pairing above TC or some necessary broken symmetry state. So this energy scale is much larger, as high as 2 delta over kBTC of 25, which is a factor of 4 difference in these two measurements. Finally, for Andreev reflection, we found that a nice probe for unconventional superconductivity, superconductivity defined by an anisotropic pairing mechanism, is to look back in the literature and find other people who did point contact spectroscopy on correlated superconductors. So here is UPT3. This is a candidate F-wave superconductor that was analyzed by the Janssen and the Taillefer group in 1993. You can see they're plotting differential resistance instead of differential conductance. So you see a dip whenever there's Andreev feature, the resistance dips because of the superconducting state. And they found that, in BTK theory, which describes point contact spectroscopy very aptly in superconductors, the area of this deviation here. So this deviates from the normal state with some excess current at low bias values. We call this the excess current, and this is due to the superconducting state. That more current can flow through a superconductor because of Andreev reflection than when it's in the normal state. So the area underneath the curve of this Andreev reflection reflects something about the gap size. In fact, in BTK theory, in the isotropic S-wave superconductor, this is exactly the gap size. But in unconventional correlated superconductors, you find that the area normalized for this point over here, it appears linearly suppressed with temperature instead of quadratically suppressed or square root suppressed in temperature, as you would think the gap evolves. So this is pointing towards possibly some inelastic scattering from bosonic modes. This is how this was interpreted in UPT3, and those bosonic scattering modes start at very low temperatures and suppress the excess current to this sub square root function here, highly linear function. One important assumption of this hypothesis is that the order parameter in UPT3 needs to change as a function of angle along the Fermi surface. So it needs to have nodes in the system in order for these bosonic scattering scenarios to be pair breaking. We observe something very similar in magic angle graphene using point contact spectroscopy. If we vary the temperature and fit using the BTK theory to a nodal hypothesis, then we can extract out, not only the gap, which follows this gap trend here from the Andreev reflection, but we can also just integrate the excess current below the curve here. And we find that it really aptly follows this linear dependence, which shares the same TC here. So it's not that we're probing something different, we're just probing it two different ways. One is by probing directly the gap shape via fitting the Andreev spectrum, which really gives us the right TC in the sample, and then probing this so-called excess current, which may be suppressed by inelastic scattering of bosonic modes. I think that there are many bosonic mode candidates in magic angle graphene, ranging from something kind of conventional like phononic modes to something more unconventional like isospin fluctuations. And so it would be good to know what is going on here. Why is this excess current being so heavily suppressed at low temperatures? And to know if, to know this may shed light on the order parameter, which again, if this is due to pair breaking from inelastic scattering, this needs to be accompanied by a sign-changing anisotropic order parameter, which is consistent with our tunneling and our point contact spectroscopy measurements. So now that we have this probe, this combined scanning tunneling spectroscopy and point contact spectroscopy probe, we can analyze the difference between the critical fields and critical temperatures, and we find a strong deviation, a strong departure from one another, indicating a kind of a pervasive pseudogap regime in the system. So I'll remind you that PCS is measuring the coherence of the system, and we identify critical temperatures of about 1.2 to 1.3 in our devices, very consistent with transport experiments. However, if you probe spectroscopy at high temperatures, you'll find that spectroscopy generically is partially gapped at high temperatures, something like 2 or 3 times higher than the TCs measured in our transport experiments. You can find this suppression of the density of states up by 4 Kelvin, as high as 5 Kelvin. I think I've seen this as high as 6 or 7 Kelvin in some situations, but the data quality is not quite as good, so we saved it for the supplement. But we're confident that this gap doesn't go away at TC, and it's indicative of a pseudo gap regime where we know that there's no phase coherence here because we can measure phase coherence using PCS. I think what's more remarkable is that, you know, the critical field of the system is quite small, about 15 millitesla to 200 millitesla in one of our best devices. This is kind of natural for a very, you know, low temperature 1 Kelvin superconductor. And yet, when you do spectroscopy on these systems, the gap doesn't go away at, you know, as high as 1 Tesla. In several Tesla fields, it changes, but it doesn't go away. You can see that at 0 Tesla and 1 Tesla, the gap feature gets a bit broader in the coherence peaks, and the minimum of the spectrum pulls up a little bit. But largely, they're very similar to each other. And this pseudo gap regime persists to, you know, 0, 3, possibly even 6 Tesla. When it starts to get involved with churn insulators, it becomes very difficult to tell what's going on here. So I'm very confident that it's at 3, 4, 5 Tesla. But once the churn insulators come in, they also present gap features. And it's very hard to distinguish the two without a probe for pseudo gap physics, where there's no coherence that's seen in this system. But pseudo gap regime persisting to much higher than more than an order of magnitude higher than BC is really unprecedented, and it shows this kind of pervasive pseudo gap regime in both high temperature and high magnetic field. So I'd like to conclude with a little preliminary data that we've shown in our manuscript, where we've done the same probe, scanning tunneling spectroscopy and point contact spectroscopy on an aligned device, a device that is magic angle graphene twisted to 1.08 degrees, and it's aligned to its underlying boron nitride substrate. A little discussion about topology in magic angle graphene. Magic angle graphene, it consists of a number of Dirac nodes that are inherited from the graphene layers that they're made from. And these Dirac nodes are protected by a composite C2T symmetry. This is 180-degree rotation and the spinless time reversal symmetry. And in the non-interacting picture, these Dirac modes carry all the Berry curvature of the system of pi. There's a pi Berry phase in the K valley and a minus pi Berry phase in the K prime valley. So there's this incipient topological character in graphene. And early experiments have shown that when you take magic angle graphene and you align it to its boron nitride substrate, you forcibly break one of these symmetries, namely C2 symmetry, that boron nitride is made up of 2 different atoms with different electrostatic potentials. They emit electrochemical potentials on magic angle graphene and forcibly break the rotational symmetry of the system. So what happens is that these Dirac cones, they gap out, they impart their Berry curvature onto emergent churn bands, and then first observations from David Goldfaber-Gordon's group at Stanford and follow-up experiments from the Young group at UC Santa Barbara have shown that if you partially fill one of these flat bands, you hope that electrons will take the bait, they'll valley polarize into an asymmetric population of churn bands and emit a quantum anomalous Hall effect. So this is exactly what they do, and they measure, you know, the Young group specifically measures a quantum anomalous Hall effect within 0.1%. It's really beautiful data and kind of a striking observation in a system that has no magnetic atoms. This is just carbon, and this is one of the first examples that I think the field has seen of an orbital ferromagnetic state with a quantized Hall conductance. So we probed one of these samples. We're trying to figure out, you know, what is the intuition here? When you have graphene aligned to boron nitride, you see kind of dark regions in topography that are surrounded by these light rings, which signify carbon-boron regions that are lattice relaxed. These are the favorable regions where carbon atom sits on top of so a carbon atom sits on top of a boron atom, and then the other carbon atom sits in the middle of the hexagon here. So this is under lattice relaxation, this is favorable, and it forms this kind of triangular lattice of dark patches. But then you have the triangular lattice of the graphene moire, which presents bright spots here. And so, you know, here's an early experiment on CVD grown graphene from my coworker Dylan Wong when he was a grad student at Mike Cromie's group, where they see that when you have 2 different length scales, you generically form this super lattice in the system. That there's at low wavelengths, around 4 or 5 nanometers, you find this kind of long wavelength beating pattern between the 2 moire scales. So this is kind of what we expected in this sample, and it's actually very strikingly not what we saw in magic angle graphene. So it ends up that when you take magic angle graphene, which has a wavelength, a Moiré wavelength of about 13 or 14 nanometers, and you align it to its boron nitride substrate, graphene boron nitride has a wavelength that's very similar, about 14 nanometers at perfect alignment. And so the Moiré scales actually snap together, and they snap together for these large patches where it's uniform again. You maintain Moiré commensurability. This incommensurate commensurate transition occurs where the two length scales, they snap together and place AA sites in the middle of the carbon boron regions here. So they look kind of like bees and little bee holes, and it's kind of funny to see these here for the first time. We were really unexpectedly stumbled across regions of our device where we found this. You can do structural characterization by varying the set point of the STM tip. STM works where when you take a topographic image, you integrate over the density of states from your set point, your voltage set point, up to the Fermi level. So when I set 300 millivolts, minus 300 millivolts, I'm probing the occupied states in STM up from 300 millivolts to the Fermi level. So you can see the combination of the two structures here. And then as you pull into the Fermi level, you find density of states much closer to the Fermi level. These are the flat band states. So this should tell us something about the twisted bilayer graphene structure. And you see all of a sudden in topographic images, the bright AA spots that we know are magic angle regions here. If you depopulate the system, so if you move the flat bands above the Fermi energy, now when the set point integrates from a low set point to the Fermi level, there are no occupied flat band states. And so the only characteristics that you see are those of the graphene boron nitride Moiré. So we can see, the two structural images tell us the nature of the stacking in this composite system here. So when you perform, scanning tunneling spectroscopy and point contact spectroscopy on these same devices, you find insulating phases at nu equals 3 and nu equals 2. With a small field analysis, we find that this nu equals 3 is a zero field churn insulator with churn number equals to +1, just like Andrea has seen, or Andrea's group has seen. And then this is a topologically trivial insulator that forms that nu equals 2. Indeed, we find a very large gap feature at charge neutrality, indicative of a strong C2 breaking in the system. And we find that although there's a very large density of states at the Fermi level in the range where people have seen superconductivity, it just pins. There's no pseudo gap. There's no superconductivity even at our lowest temperature of 200 millikelvin. So our sample is low disorder. It has low strain. It has nearly perfect magic angle, and yet we see nothing in the lower band. It just kind of sits there. So I think there are two interpretations that are circulating in the field right now, and I hope that our structural analysis will and our spectroscopic analysis will finally tell us something about this. When Transport claims that their devices are aligned to the boron nitride substrate, they see some features in the gate tunable conductance, but here I can look at every atom. I can see that it's completely aligned and exactly how it's aligned to the boron nitride substrate. So this is a lot more information, and we're very confident that this is not superconducting when it's aligned to the boron nitride substrate. So it may not be superconducting because this IC structural transition disrupts electron-phonon coupling. Now I have a very different structure, a very different mechanical structure to the system. So the phonon dispersion is likely very different in electron-phonon coupling in the system. If it is phonon mediated, it may be disrupted. So, phonon theories of superconductivity exist from these two references, and these papers that discuss screening and MATBG may be favoring the phonon mediated story. In contrast, alignment to boron nitride breaks one of these necessary symmetries that this symmetry that may be necessary for superconductivity in this system, C2T. We see the hard gap at charge neutrality that is accompanied with strong C2 breaking. In all of our other MATBG devices, we see a semi-metallic behavior, which is showing that this symmetry may be preserved in those other devices, but absent in this device. So here's a C2T symmetric theory for superconductivity, and some experiments on magic angle twisted trilayer graphene point us in this direction, which is also a twisted graphene superconductor, which also has this symmetry. So a bit of summary and outlook. We've observed a number of pieces of evidence, a total of 8 that I can count, that superconductivity in magic angle graphene is unconventional and quantitatively inconsistent with the BCS theory. I'll remind you that the tunneling gap that we observe is absolutely enormous, admitting a local pairing criterion of about 25 at its largest values. The tunneling gap and the Andreev gap are both best fit by a nodal gap function using BCS and BTK theory, respectively. Fitting these two gaps tells us that there are actually two different energy scales. Not only is the tunneling gap very large, but PCS is larger than the BCS prediction, and they are off from one another by 4 orders of magnitude. There's some precedent for this in underdoped cuprates, and so we draw parallels to this in our paper. And then finally, the PCS excess current we see as suppressed linearly with temperature, which is in sharp contrast with the quadratic behavior you expect from a conventional non-sign changing order parameter. We observe this high temperature and extremely high magnetic field pseudogap regime, and both of these phases, both of these ground states are destroyed with HBN alignment, despite the very large density of states that we see at the Fermi level. It's signifying that there's something more to go on with superconductivity at this filling. So a bit of outlook here. We're about 3 years out from Pablo's original observations of superconductivity in the system, and by now we know a ton about superconductivity. There are many transport experiments and this first spectroscopic perspective on the system in this ground state. And I think it's about time that the community is able to answer some of these questions here. So I've listed, what are the superconducting mechanisms that we all proposed 3 years ago that emit nodal gap functions, nodes in the wave function that are highly suggested by the data that I've presented today. In addition, what's the nature of the pseudogap regime? So in the cuprate superconductors, people have discussed notions of preformed pairs or competing or intertwined orders. These are interesting ideas, and to see what is compatible in the current literature for magic angle twisted Bilayer graphene would be an interesting outlook. In addition, we want to relate our current experiments, to the existing literature. Namely, what is the relationship between our observations of robust superconductivity, this unconventional superconductivity, and the existence of superconductivity in the presence of moderate screening, as these transport groups have seen. And in addition, kind of a little bit more broadly, what's the relationship to the strong Pauli limit violation that it's observed in twisted trilayer graphene? Twisted bilayer graphene and twisted trilayer graphene have very similar band structures, and so there's kind of a growing notion in the community that they may have similar pairing mechanisms. And while a Pauli limit violation can be explained by spin triplet superconductivity that may or may not be consistent with the nodal gap structure that we observe, a Pauli limit violation can also be explained by a very large pseudogap regime. When pairing is not dictated by TC, but by a very, very large energy scale, much larger than BCS prediction, then the expected energy scale that you need to overcome via Zeeman splitting is much larger. And so we should call into question whether or not this hypothesis makes sense, given the very large pseudogap regime that we observe. In conclusion, I'd like to thank my collaborators, Myung-Chul Oh and Dylan Wong. These are postdocs that we did all these experiments with. And again, Myung-Chul Oh is the lead author of this paper and really deserves it. I'm so thankful that I've been able to work with these two guys. Ryan Lee has just joined our group and has helped us with recent experiments and has been really essential for us to complete the experiments on these at these final moments on superconductivity and magic angle graphene. And then, of course, I'd like to thank my advisor, Ali Azdani, for his insight and his support and really everything that he's done for this project from day one. So thank you very much.